Hey, here's my history of calculus book. Well, it's a day before my thing is due. I should probably get started. Let's see what it says here. Oh, so the main ideas that are part of calculus started a very long time ago. Some of the first steps were taken by Greek mathematicians, and one of the most important ones is Archimedes, and he did this in around 225 BC, and his advance was to show that the area of a segment of a parabola is 4/3 the area of a triangle with the same base and vertex, and 2/3 the area of a circumscribed parallelogram. So Archimedes constructed an infinite sequence of triangles starting with one of area A and continually adding further triangles between existing ones and the parabola to get the certain areas, and this was the first example of summation in an infinite series. And he also used like the method of exhaustion to find an approximation of the area of a circle, and this is also another example of integration. Oh no, it seems like there are some pages missing in the history of calculus. Oh no, what will I do? I guess I will have to go and try to find them. Okay. Yep. Look, I found a piece. Let's see what it says. Wow. So no further progress was made until the 16th century, when mechanics began to drive mathematicians to examine problems such as the centers of gravity. Kepler, in his work on planetary motion, he had to find the areas of sectors of an eclipse. His method consisted of thinking of areas as sums of lines. Oh wow! Wow! Another form of integration. So, another mathematician was Roberval, and he looked at the area between a curve and a line as being made up of infinite number of infinitely narrow rectangular strips. Isn't that amazing? And another one. Yes! Let's see what it says. So there were two more mathematicians, Torricelli and Barrow, and they both considered the problem of motion with variable speed. Wow. So the derivative of distance is velocity, and the inverse operation is taking one from velocity to the distance. Wow. The inverse of differentiation began to involve naturally, and the idea of integration and derivatives were inverses of each other were familiar to Barrow. In fact, Barrow never explicitly stated the fundamental theorem of calculus, but he was working towards the result, and Newton was to continue the direction and state the fundamental theorem of calculus explicitly. Wow! Oh my gosh! Look, there's more. Awesome. Let's sit down and see what it says here. Oh. All right. So, another mathematician that was involved in the creation of calculus, and a very important one, was Newton. So Newton wrote a tract on fluctuations in October of 1966. So this was actually a work that was not published at the time, but seen by many mathematicians, and had a major influence on the direction that calculus was going to go towards, including Newton thought of a particle tracing out of a curve with two moving lines, which were the coordinates. The horizontal velocity of x prime and the vertical velocity of y prime were the fluctuations of x and y associated with the flux of time. The fluents or flowing quantities were x and y themselves. With this fluctuation notation, y prime over divided by x prime was the tangent to f of y comma x comma y equals 0. So also in his 1666 track, Newton discusses the converse problem. Given the relationship between x and y prime divided by x prime and y, to find y. So since the slope of the tangent was given for each x, and when y prime divided by x prime were equal to f of x, then Newton solved the problem by anti-differentiation. He also calculated areas by anti-differentiation, and this work contains the first clear statement of the fundamental theorem of calculus. But there's more. So there's another mathematician who was had very similar work to Newton, and he was from a German province, and his name was Leibniz, and he was very conscious of finding good notation. Finding a good notation was of fundamental importance, and thought a lot about it. Newton, on the other hand, wrote more of the calculus just for himself, and as a result, he just wrote whatever notation was on his head. So many of Leibniz's notations in calculus are still used today, such as the squiggle when you integrate, which is the operator aspect, and what his notations were a big part of calculus. And then a few others helped develop calculus, but they are of lesser importance.